Hi, this is Miss Litton, and this is still my period 1. Say hi. Hi. All right, so we are continuing on our Chapter 6 discussion, Metabolism, Energy, and Enzymes, and we are now focusing on metabolism. So, catabolism and anabolism. When I see anabolism, I think of bad people doing what? Anabolic steroids. Yeah. What? Is that what, I don't know what you're thinking. I don't want to know what you're thinking. Okay. I'm glad. I don't want to hear it. I don't want to hear it. So anabolic steroids, people are taking steroids. What are they trying to build up? Muscles usually, okay? So if you remember anabolic steroids, if that helps you in building, okay? Maybe you think catabolism, breaking down, like a cat running crazy around your house is breaking things down. I don't know. Okay, so large molecules going to small molecules, you're going to release energy, and you should be able to tell me why. Because you are breaking what? Bonds. So you're releasing energy. So if you want to take small molecules and make large molecules, you have to make bonds. So that's going to require the input of energy. Hence, exergonic, endergonic, right? Endergonic, bringing it all together. Circle of life, Simba. Endergonic reactions are going to require the input of energy. Exergonic reactions are going to release energy, okay? So on your, wherever you are, metabolism is the sum of all the chemical reactions that occur in a cell. The sum of all the chemical reactions that occur in a cell. Metabolism, the sum of all the chemical reactions that occur in a cell. Oh, I'm still here. Anabolism or anabolic pathway, consume energy to build complicated molecules from simpler ones. To build complicated molecules from simpler ones. Catabolism or catabolic pathways leads to the release of energy by the breakdown of complex molecules to simpler compounds. Leads to the release of energy by the breakdown of complex molecules into simpler compounds. Not it. Okay. Whoever is not it, pass or play, explain this in 3 terms that are represented here. Go.
Release of energy by breakdown. It's probably like small molecules. What do you guys get for number 3? Release of energy by the breakdown of smaller okay. Explain. Okay, so catabolism, it's you're breaking the bonds, so that you're breaking bonds. Then, like
it's like dehydration and hydrolysis synthesis together without water, basically.
Okay, we good? Okay, so far easy peasy. Are we all right? Okay. So now, reactants versus products. Whoever just explained this right here, I need the other bio buddy. I don't think you're going to have any trouble. Explain reactants versus products. Go ahead.
Reactants is basically like fighting for the energy.
I want to get additional products. Is this products are what you make reactants?
Yeah. Like glucose and oxygen.
Okay, now, my bright and wonderful students, this was reactants and products for photosynthesis. What is the reaction? You and I don't do photosynthesis. What do we do? What are our reactants for cellular respiration?
Glucose.
Ah, so the products of photosynthesis are the reactants for or cellular respiration. And our products, what do we end up making? Yeah. You do. You shine bright for all the world, like a diamond. Okay? So our products are carbon dioxide and water. Now, sunlight's just a form of energy, right? So what product do we make? ATP. Right? Okay? Put it all together. So reactants participate and products form as a result of the reaction. Reactants participate and products form as a result of the reaction. Do you remember when we discussed potential energy? Yes. What has more potential energy for us? Glucose or carbon dioxide and water? Glucose has more potential energy. When you want to measure energy, okay, we're going to measure it using G. And if we put a delta in front of it, what does that mean? Change. And this is a change in free energy. And free energy, another word for that would be useful energy. Okay? Energy that is free to do work. Because not all energy is free to do work, right? Look at me. Look at me. I'm moving, so some of that energy I'm moving my muscles, but some of it I'm losing that energy as what? Heat. That's not useful energy, right? So free energy is the energy that's actually available to do work. So the amount of energy left to do work after chemical reaction has occurred, we're going to call this delta G, and it is measured in what? Kilojoules. Sorry, did I have that in your notes? Measured in kJ. Hey, do I have number 5, Gibbs free energy equation in there?
Yeah.
Okay, good. All right, just check. All right, let's take a look at this picture right here. Okay? You have already learned this. We have already discussed this, so this should be a review. Come to me, so I just eyes up here, and then you can snap and do whatever you want to do. So we have 2 reactions here, exergonic. What do we hear in exergonic? Exit, right? Okay. And endergonic, I'm thinking in. I'm measuring the amount of free energy, right? We've put a ball rolling down a hill, but we can relate this to a graph. In an exergonic reaction, I started here. I am ending here. There has been a change in the amount of free energy. It has gone down. So if I had this much, and now I have this much, my delta G, my change in free energy, is going to be equal to a what kind of number? Negative, because I have, in fact, lost energy. I had potential energy was the ball at the top of the hill. I have potential energy. It's rolled down. Now I've lost that energy. So that is a delta G that is negative. Okay, now, youngest bio buddy, you make the argument for what's happening here in B, based on what I said in A. Go ahead.
It's like, there's like, you gain potential energy, and you gain free energy as the reaction takes place. And the amount of energy goes up, and then you gain potential energy from the product.
Okay, now, that ball is not magically rolling up that hill, right? Somebody had to input energy into that system to get that ball to roll up that hill. Do you agree with me on that? So the energy that was here in this person is now been transferred to this, because now it's going to have potential energy once it's up at the top, right? So the products now have more energy than the reactants. The ball started here, and now it's here. Started at the bottom, now we're here, right? So now I have more energy. That is an endergonic reaction. Okay, not it? Not it. Okay. Whoever won, one of you is going to explain the actually, no, I take that back. You're not it, and this is worthless at this point. Whoever explained this reaction right here, don't explain it on the next page. You'll see. Okay? Switch the roles up a little bit. Here you go. Go ahead. Go ahead. You can do this. I know you can.
The reactants are you need energy and
I tried to do something with the dots. See if you can follow what I did with the dots.
Okay, so like it goes from a bigger molecule to a smaller molecule that requires the loss or release of energy, and like the reactants have more energy because you have those bonds. Whereas here, you're trying to make those bonds, so you require the energy to make it into like a larger multiplier.
If the dots represented free energy, do you know what I did with the dots? Yeah, so here the reactants had more energy and the products had less.
Could this be like a decomposition reaction?
A what?
Like different decomposition, kind of like if there's more energy, like is that like too small?
Wait, no, I just don't think I understood what you said.
Is that could be decomposition?
Oh, decomposition.
Yeah.
Yeah, sure, absolutely, it could be decomposition. Nice. Okay, now you can see on this one, our delta G is greater than 0. We're gaining energy in this one. The products have the most energy, where here our delta G is going to be less than 0. We've lost energy. All right, on your notes, delta G is negative. What kind of reaction is that going to be called? Exergonic reaction. The loss or release of usable energy. The reactants have more energy. The reactants have more energy. Whereas in delta G is positive, what kind of reaction do we call that? Endergonic reaction. Input or gain of energy required. Who has the most energy? What are you going to put in the next spot? Products. Good. Products have more energy. All right, ask your bio buddy, are you in the Shadowlands or Sunshine? Okay, now, remember our equation sheet. Be to me. Our equation sheet, okay? In the bottom right-hand corner, I think it's the back side, one of your equations to understand is Gibbs free energy, okay? So you already got the delta G part down, right? You know what that is? That's free energy, the amount of energy I have. Okay? Then we have delta H minus T. What do you think T stands for? Temperature. And then that temperature is multiplied by delta S. Well, you know what S is. What is S? Entropy, right? So on delta G, change in free energy. Delta S is change in entropy, you've got that. Delta H is change in what? Enthalpy, and I'll talk about that in just a minute. And then T is temperature in Kelvin. Take a look at this right here. Okay, so your overall amount of free energy, and again, you don't have to memorize this equation. I'm just kind of walking you through. I want you to understand why you would see a negative delta G. If I have a number here, okay, so your enthalpy is going to be positive for endergonic reactions and it's going to be negative for exergonic reactions. So look on your little equation sheet that I gave you in your notes. Enthalpy is measured in joules. It is the total what? Energy. The total energy of the system. Total energy. So think about it. If I have an exergonic reaction, what has happened to my energy? It's left, okay? So I'm going to have more of a negative value for an exergonic reaction and a positive value if it's an endergonic, total energy, okay? That's the whole energy. I don't know if that will help you, even though whole starts with a W, okay? Now, if I take that energy and I subtract off the amount of disorder I have, well, if it's already an exergonic reaction, I have gone, if it's an exergonic reaction, I've released energy, I've gone to even more disorder, right? So I'm already a small number, and now I'm going even more negative by taking into consideration all the disorder. And if your temperature is higher, do you think I'm going to have more disorder or less disorder? More, because all the molecules are going to be moving what? Faster. So I'm going even to greater disorder. So just think, I'm already lost energy and I have more disorganization and a higher temperature. I'm moving faster. This is going to be a very negative number. That's what you want to see there. Now, the opposite of that would be true for an endergonic reaction. My whole system will have more energy. I'm going to more order, less disorder. So this number right here, change in S will be very small, right? I'm going to less disorder. Now, I don't want you to get lost in this. It's kind of a, you haven't gone into enthalpy, you haven't gone into the chemistry yet. I just want you to see where delta G is coming from. And if you look, I gave you a great link to review this, and that goes to a Bozeman video just on Gibbs free energy. I think it's about 10 minutes long, and like all the videos I put in your calendar, tell your bio buddy how good, how disciplined have you been in watching those videos in preparation and review.
Oh boy.
You followed it, okay? Tell your bio buddy right now, how disciplined have you been in your reviews? Go ahead.
Pretty good.
So, what type of reaction do you think is going to be spontaneous? An exergonic reaction or an endergonic reaction? Exergonic. Now I want to tell you, based on that premise alone, you should be falling apart in your chair because you're super complicated and organized, right? So if exergonic reactions are more likely to happen, you should just be falling apart, right? Going to greater and greater disorder. Here's the deal. There's a, you're not, which is good, okay? There is a little, we're going to be talking about this, what we're leading to, what I want you to see in the bigger picture. There's a little hurdle of energy that you have to cross before you go follow through with your endergonic or exergonic reaction. That little hurdle of energy is called the energy of activation, and it prevents you from just falling apart. So overall, you may have a change from a higher energy state to a lower energy state, but there's a little hurdle you have to go through first, which prevents you from falling apart. There's a little endergonic reaction before the big exergonic reaction. For instance, I could have a fireplace and I could put kindling and paper in it and wood. Does that have a lot of potential energy? Mm-hmm. Yes. Does my fire immediately spontaneously break down and immediately I have a fire in my fireplace? No. What do I need? Yeah, I need just one little match, right? Because once I get the potty started, that thing's like that. I start to light the paper and then boom, 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 and it's, right? And so then I will go overall to that exergonic reaction, but there's that little hurdle first to get the party started. Okay, and so that's what we're going to with enzymes. Enzymes are like that match to get the reaction going, but a very specific one, and we'll go more into that. I just wanted you to see big picture. Why don't you riddle me this? Besides him losing his hand and a few fingers. See, where's his hand? We can't find it. This actually happened to my chemistry professor when I was in high school. Not when I was there, but like, he did this in an experiment in front of his class. He blew off some of his fingers, and they were actually stuck to the ceiling tiles. No, they did not. Okay, Panic at the Disco. Please get a hundy. Wow.
Let's go.
My friends, this is an explosion. It is a release of energy. So overall, it's going to be a what kind of reaction? Exergonic. Please check with your bio buddy because we're still struggling a little bit. Look at their clicker, have a discussion. Let's go.
I was gonna look
You literally grabbed my clicker and looked at it and then put your answer. I didn't know what I said. Wait, wouldn't it be because technically, wait, wouldn't you have to like require energy like
Now, did we need to do something to have the explosion happen? Yes. So you might have had to, like I was kind of discussing right before this question, put in a little bit of energy to get the party started, but clearly overall you have a release of energy, right? So overall it's going to be exergonic. So let's talk about the energy currency of our cells. For us, it is ATP. It is the dollar bill of our cell, okay? Glucose is like $100 bill. ATP is just $1, okay? And in the process of cashing out that $100 bill to singles, that's basically cellular respiration. We just don't have a very good exchange rate. It'd be like me coming up to Max and going, Max, I need some singles because I want to go use the soda machine. I only have 100. Can you break this for me? He goes, yeah, sure. But I have like a $39, so take it or leave it. And I'm like, okay, I really want the soda, so I guess I'll take the singles. And so I'm desperate, right? So there is a loss there on my part of usable dollars, okay? There's a loss there. So that would be due to what law? Second law of thermodynamics. So there's a loss of usable energy. But I've got to try to get to ATP. We already know about the structure of ATP because we learned about the 4 important organic molecules. So I would like the light-shirted bio buddy to explain the structure of ATP. Go ahead, light-shirted bio buddy.
So ATP is 5 sugar carbons, it's got it's got 5 carbons, and then it's got phosphate.
yeah, so
5 carbons.
yeah, that's called 5 carbon sugar. It has adenine plus adenine plus something equals adenosine.
Adenine plus 3 phosphate.
No, there's something else to make it adenosine.
Adenosine plus 3 phosphate.
Okay?
Yeah, but what
So
adenine and
how much energy do we get out of it? When you break off a phosphate from ATP, you get 7.3 kilocalories of energy. That goes in your number 1. Okay, and we have the structure of ATP. It's adenosine, which is an adenine and a ribose, plus 3 phosphate groups. Now, here's the beauty. When we already understand about exergonic and endergonic reactions in ATP, okay, what we want to do is we want to take energy from something like glucose, okay, and we want to burn that glucose, and in order to do that, when we burn the glucose, we will transfer the energy that is in the glucose into ADP so that we can form what? ATP. Okay, dark shirted one, you're on for this. Go ahead.
glucose, amino acids, and anabolic reactions transfer energy from ATP and do the second law of thermodynamics. And complex molecules such as polymers, like catabolic reactions.
Okay, so come back to me just for a minute. When we go from simple molecules to more complex molecules, is that about building or breaking? Building. What's the name of the reaction for building? You already learned it. Dehydration synthesis. Do you remember when we said all reactions, though, you require an enzyme to do it? Remember that part? So dehydration synthesis, to generate a more complex molecule, it's going to require an enzyme, and it could require also ATP in that process. The breaking of that molecule, breaking it back down, what do we call it when we break it? Hydrolysis. Good. We can use the energy that was in those bonds in order to do the opposite, to synthesize ATP. And most of the time when we think about metabolism, we think about our own enzymatic reactions, our metabolic rate of our body, and how fast or easy we burn fuel. You have heard people say they have a high metabolism or they have a what? Low metabolism. Generally speaking, people who have a high metabolism tend to be what? Skinny, because they're like burning, burning, burning. What are some ways you can affect your metabolic rate? Do you know? Diet and exercise. Yeah, diet and exercise. If your body knows that you will fuel it regularly, it will have a high metabolic rate. Here's the rub for those that choose, for one reason or another, an eating disorder. When it's the one where you have anorexia and you're not eating at all, okay, when you limit your calorie input, what do you think is going to happen if you limit the amount of gas you put in your car? It's going to run slower till it stops altogether. Okay? You are like that. If you're not giving yourself regular food, then your metabolism is going to slow down. Okay? That's the way it works. So if you want to have a high metabolism, you need to fuel your body. You just have to be careful because sometimes people overfuel their body, right? Okay? I made last night homemade ice cream sandwiches. So I made homemade chocolate chip cookies, and then I got vanilla ice cream and put it in between. But they didn't get hard in time, and the ice cream smushed out. I think they're fine this morning, but I ate it anyway. But anyway, if that's all I ate was ice cream sandwiches because I thought they were good, and chips and guacamole, that would be, and bread with butter and melted cheese, okay? Just those things, okay? If that's what I eat regularly, that might not be good fuel, and I could get too much fuel. But it is a good idea to have breakfast, a snack, lunch, a snack, dinner, and a snack. Your snack just can't be a whole cheesecake, okay? All right? But if you don't give yourself enough calories, then your metabolism is going to slow down. Do we have some genetically programmed? Yes. We're going to learn about our thyroid gland secreting thyroid hormone, which is going to regulate our metabolism, and some people might have trouble with their thyroid, and so their metabolism is slower. That's all part of that process. This, when we talk about metabolism, we are referring to that. Those are all the enzyme-mediated reaction, but that specifically for a lot of you, you're thinking about food and fuel for our body. Okay, so I want uncoupled reactions. ATP hydrolysis can be coupled with an endergonic reaction so that energy loss is minimized. ATP hydrolysis can be coupled with an endergonic reaction so that energy loss is minimized. So here you're taking C and D and you're trying to make this product A and B, whatever that is. And this reaction to form A and B, what could you tell me? What kind of reaction must this be if I'm forming A and B? Exergonic or endergonic? To form A and B, exergonic or endergonic? Endergonic. Why? It's requiring the input of what? Energy. So I'm releasing energy from ATP and using that energy for this endergonic reaction of regenerating A and B. I'm coupling them together. An exergonic reaction coupled with a what? Endergonic reaction. Okay? So coupled with an endergonic reaction so that energy loss is minimized. Whoever explained this picture, I need the other bio buddy to explain this picture. Again, review. Go. Remember, this is spinning this way in this picture.
Yeah, and that forms ADP and P because you're breaking the bonds of
An endergonic reaction requires energy.
Yeah, and you put plus P and then energy and you get ATP. So basically a cycle of like breaking down adenosine triphosphate into adenosine diphosphate and phosphate or phosphorus.
Okay? That's a good slide, a good review. Okay? So, as I said before, glucose is like $100 bill, not a single. Okay, and just like I gave you that example before, you're going to convert that glucose into ATP, but our body, efficiency-wise, about 39% of that energy is captured from glucose and transferred into the bonds of adenosine triphosphate. So on your notes, as glucose is hydrolyzed through cellular respiration, ooh, those are words you understand. As glucose is hydrolyzed, what are you thinking about? Hydrolysis breaking. ATP can be what? Synthesized from ADP, an inorganic phosphate. Only what percent efficient? 39% efficient. So how much is lost as heat? 61% lost as heat. So now let's segue. What are you using this ATP for? What kind of work are you doing with your ATP? So here's 3 big examples of what you might use it for. It could be for chemical work, to use the ATP to synthesize molecules in your body. Maybe you're rebuilding your muscle after exercise. So chemical work used to synthesize macromolecules. We have had a big discussion about cell membranes and transport work, right? And pumps, and how pumps require ATP. We talked about the sodium-potassium pump. And this is when you're concentrating things against the what? The gradient. Good. Did you get your hair cut? Looks super cute in a non-creepy teacher way. Okay, so transport work used to pump substances across a membrane. Watch out, she is really working hard lifting that 2-pound weight. Mechanical work is used to permit movement. Used to permit movement. Like flagella or chromosomes to move or your cytoskeleton. Yes?
Is this just mostly the functions of ATP inside the cell?
Yes. All right. Not it. Okay, look. Not it. Pass or play. Somebody needs to look over metabolism and ATP. One bio buddy needs to give a metabolism summary explanation. One bio buddy needs to give an ATP summary explanation. Go ahead.
I don't care.
So metabolism is basically the sum of all the chemical reactions that occur. It can be divided into 2 categories, anabolism and catabolism. Anabolism is like you require energy, it's like endergonic reaction to build all these molecules. And catabolism is the breaking down of these large molecules of energy.
They release 7.3 kilocalories of energy. Its structure is adenosine plus 3 phosphate groups. They couple with endergonic.
I wanted you to go fast. You can do this. Please focus.
What do you think I got?
Here we go. Slipknot, the gorillas. I believe in you. Jeremy, did you do it right? Please. Yay! Oh, look, there's a 1. First of the day. Okay, here we go. Here's another one. Let's focus.
If we get through, we'll meet our record.
Okay, people, you work hard on this. Come on now. It's loading now. You can do it.
I didn't get the question.
I believe in you.
Here it comes.
There it comes. It's coming.
Hi.
Okay.
It's
Come on.
decreasing exponentially.
Do it.
It's gonna be.
Come on now. Okay. This could be your record breaking.
Oh my
Oh!
Wow.
2 of you did it. System of Down, Fallout boy. Yeah, they just need attention. Get a hug before you leave home. Could have been 3. That's where you could have been. Could have been 3 after this. No, back to 1.
I think it's D.
Go, people.
Oh, I do. One of us will be friends.
Not really sure what to tell you on this one. It is all of them. Check your Bio Buddies clicker, chastisement or praisement. You got 1. Oh, you're number 2?
Yeah.
Okay. Guys, what do you need to bring next class? Lab notebook if we have time. What are we going to do next class? Quiz. What else? Finish the notes and then whatever time we have in the lab. Look at me. Look at me. Shh. The more familiar you are with the notes next time, guess what? It'll go what? Faster. I got the impression today that you weren't familiar with these notes. You probably were working on your lab. I understand. You have time. Please get familiar so we can move a little bit quicker next time. Okay? All right. Love you very much still.